So yes, in the file that I've shared, you will see basically everything that we have done. Actually, this is a clean version of the study file that I have for this course. Everything is looks so neat and clean, but except from this part of the definition where you see some intricate wire system. Normally, when I see this, in Grasshopper, I try to keep things clean by creating some wireless connections because I don't like this kind of messy aspect. But um, it's not like this. I mean, when you design something like this complex, well, it's always a trial and error process. Nevertheless, I wanted to point out a couple of things. You see that this is something that we didn't discuss yesterday. And actually, I also made a quick implementation today, this morning, before connecting. So there is a block, a group here inside this purple definition for this multi-story building, which is called fancy roof. Fancy because, well, first, it might also be ugly roof eventually, but in order to don't use a standard roof, because you see that in Revit there are also roof instance and roof type. So this works exactly like in Revit architecture. Okay, so there is no major problem in using these things, and the workflow is absolutely identical. So you take the instance, you take the type, you go here and populate uh, this component, and the roof type works exactly like a floor type. So there is no major issue in working with this workflow here for creating roofs. And actually, in Revit architecture, roofs are more or less um, floors. Um, so basically, I prefer to create a different roof, something like a vault here, which is held by two truss beams, two huge truss beams, like with an arc shape. So I wanted to point out this process, not because it is relevant in this project. Nothing is relevant in this project, maybe except from the stair, which is something that requires some tweaking, as you have seen yesterday. But just because you will have an idea of a different approach to another type of structure, which are the trusses. So there is a part of hard work that normally you can recognize in Grasshopper because it's a long line of components. When you see this, you mean you are doing some hard work, not particularly interesting in terms of conceptual meaning. But yes, basically, let me hide the final result. Let me get rid of this group. Let me hide this so you will see what happens here. This is basically the same structural rectangle that we had here at the bottom, because I wanted to place 4 vertical supports or columns here at the corner. Of course, this is not enough from a structural point of view to hold this kind of huge vault. But nevertheless, you get the point. So the important thing is the process here, not the actual result. Of course, you can tweak and fine-tune everything, but just keep in mind that this is just for understanding the process. So these are basically the 4 lines that we have at the bottom, moved up on top of this building, joined together, calculated the discontinuity. Just a quick note about discontinuity, because in order to obtain the 4 corners of this rectangle, you might also be using explode, because the explode command in Grasshopper provides both segments and vertices from a polyline, basically. So a rectangle is a polyline. So if I do this, I have exactly the same result, but also with segments. So if you need also this geometry here, you might want to use explode. But the problem with this is that as this is a closed polyline, instead of having 4 vertices, you will have 5 vertices, as you can see, because the end point is coincident with the start point. So you see that the first point is 0, 15, 10.5, and the last one is 0, 15, 10.5, the same. And so you must get rid of one, either the first one or the last one of these vertices. While discontinuity detects the change in direction, at least at this stage, only the change in direction, which happen only 4 times along the path of this curve. So that's why I am using discontinuity instead of explode in this case. But this is just some topological consideration in order to decide what's the best workflow in Grasshopper. And then I use these as start point for this vertical line, which is going to be the axis for the columns, and use their endpoints in order to obtain these couple of horizontal lines, evaluate them at the midpoint, move this midpoint up with a certain height, which is actually the same height as the floor height. So it's 3.5 actually, yeah. And then create these 2 things here, 2 arches. Okay, so this is pretty much a non-conceptual work. Okay, once you have these, you offset them. So in order to create a truss system, you need the upper profile and the lower profile axis. Everything else will be derived from these 2 curves. Now, as regards truss beams or truss structure, there are many, many things or many plugins that you might want to use and explore. I'm just going to give you a quick look at this, not because it's relevant for the workflow. I mean, the workflow, the interoperability workflow, as we saw yesterday with the component direct shape, you can basically take whatever geometry you can create in Grasshopper and send it to Revit as a native Revit element. Okay, so this direct shape component, especially this one, opens up a whole range of possibilities in terms of creating something in random Grasshopper and sending it to Revit and build platform. So what I'm going to tell you now is not important from this point of view. It's important for so that you know that in Grasshopper you can create truss systems, also complex truss system, with many plugins actually. Now, if you want to stick with geometry gym tools, there is, for example, in the Bool Ant plugin, which is this tab here, geometry gym Bool Ant, you will find this DG truss from curves and GG truss from curves length. I really hate this GG in front of every single comment, but nevertheless, this is what we have here. And actually, I am using the GG truss from curves, which is this one, that only asks for first curve, second curve. So the upper curve and lower curve, and number of divisions and truss type. Okay, so just so that you know what this thing is doing, let me hide the actual profile curves so you can see directly the result. These are only lines, of course. So it's only creating the axis for these frames. Number of divisions, you see it's basically the number of spans that you have along the beam, actually, the truss structure. So it's 16 in this case. And truss type. There are only, well, only is it's not exactly a proper term because this is one of the most complete truss creator. So you see that there are 6 types of truss structures that you can create. Now this is the default is the Pratt structure, but you can see this is actually changing the way that the diagonal and vertical elements are created along the truss. So there are symmetrical and asymmetrical beams. In this case, for example, for us, it is important to pick some symmetrical structure. So just the usual schemes. There are other commands, other things that you can do in order to create truss systems. So, for example, if you go inside Lunchbox, for example, in Lunchbox also you have these truss systems. These are 3-dimensional truss system when you see space. So you can also create very complex trusses and also 2D truss. And 2D truss, which is basically similar to this, is actually almost identical. Truss toggle is the selection for the type of trusses. And you can see that there are only 3 types of trusses. Now, remember that that geometry gym tools are optimized for structural design and analysis. So that's why you have, normally you have a more complete set of elements or possibilities in terms of structural design here. That's why you have more truss types here. But as Geometry Gym and Lunchbox, there are other tools that you can use in order to create this structure. The interesting thing from the Lunchbox plugin is this space trusses. Okay, so eventually you might want to explore also this kind of possibilities. But nevertheless, when you have created this system, you have chords A and B, diagonals, and verticals. So you can decide what type of profile you want to use for this structure. You see that I have defined two different profiles or framing types. The profiles are these, and they are both square, and they are both 0 and 0 wall, so they are thick and solid. Okay? They are not hollow profile. You can change this by defining a wall thickness. And these are the chord profile, and this is the web profile. Web profile is used for both diagonals and verticals. So if I turn on this, you see that both verticals and diagonals are included in this web profile, while the chord profile is only applied to the upper and lower profiles. And that's pretty it, because it's just framing, okay? Now, aesthetically speaking, this is not the best that you will see, because there are many things happening here that should be, let's say, tweaked a little more. But nevertheless, we are interested here in having the information sent to Revit. We are not, let's say, paying too much attention to the aesthetic of this kind of element. So the reason why we want to send this to Revit is eventually to have a parametric workflow here in Grasshopper where we can change things on the fly. And then by simply updating the geometry in Revit, that happens because of the object ID that we were discussing yesterday. Then we can change, for example, we have this change that we do here in Grasshopper. It's well, more or less in real time reflected inside a dimensional scheduled quantity inside Revit architecture. So you know, for example, what would be the final cost for these truss systems, okay, in no time. So that's the interesting thing for us. Tweaking this kind of thing here can be time consuming, and also there are some processes that you can put in place here in Grasshopper and with Revit tools, because you see that there is metering. We were already anticipating something about metering. It is basically when you have an element like this. Let's say we are looking at a beam from the top view, and then you have, and it ends in this point, right? And then you will have another beam, for example, connected here that ends in the same point, but they don't relate to each other, okay? They just end in this point. You can use metering, which is basically connecting these two beams by defining a cut plane. So if you define a cut plane, for example, like in this orientation, then the first beam will end like this, and the second beam will end like this. And so you are metering the corner, okay? And you are creating a continuous connection between these two elements, not a discontinuous connection. Now, this can be done. It's pretty time consuming, especially when you have this amount of frames, okay? It's not that automatic. You can try to do something. I would not recommend you try this with truss system, because the inclination, the orientation of the meter planes or frames is going to be extremely variable. So it's very difficult to implement this process in a truss beam like this one, an arc truss beam. Besides these truss systems, unmetered truss systems, so remember that you have this kind of unresolved nodes here, we have the roof. Now, as I'm not using the actual roof element type and instance, what I did was creating, once again, an architectural direct shape. Okay. Well, also there are these 4 support columns here, which is basically, well, they use the same column type as the lower profiles here, and they are coincident with the lower corner columns at the lower floors. Okay, so there's no problem with this. And as regards the direct shape, the only thing that you must do is define a solid geometry that you can pass to the architectural direct shape. And so in this case, I took the upper curves deriving from the offset of the original arches that we created, and then lofted them, and then calculated the area in order to have this centroid here, because I did a non-uniform scale in order to extend this roof out from the original profiles of the truss beams. Okay, so this is the only thing that happens here. You can extend this geometry however you please. And then there is this command here, offset brep. This is capable of creating a solid offset of a poly surface. This is the same one that we used for defining the solid thickness of the stair. Okay, this belongs to Parakit plugin, just so that you know where to find it. And this is creating the actual solid profile, solid shape for this roof. You could also extend the curves like a little bit here on the sides, but in the end, it's just geometry again. And then you define the roof material, and then you use the architectural data shape. And include this in the export for your Revit file. So this is the complete system for the roof. Of course, you miss several connections here. This is not a rigid structure. You should eventually create some other structural elements, but you get the point. I'm not going to re-export this because, well, basically it makes no sense. We already saw this yesterday. So unless you have additional doubts or questions, I will simply Control E these and switch to the new exercise, which is going to be somehow, let's say, a little more fancy than this multi-story building because of the shape that it has, and also a little more complex in terms of Grasshopper parametric design. There is a tricky part here that we are going to explore together. Just in order to prepare things for the export process and import process. So in order to avoid some errors in this two-step process that we are studying right now. Let me get rid of this main group here. So eventually we will be exploding this group per parts. There are several things that happen inside this definition. I don't know if you already went through it. It's quite heavy. So you will notice that by default, for example, all the paneling and the facade system is turned off. I wanted to create here a curtain wall, or yeah, something like a facade system. We are going to explore a couple of methods, not only the one that is already implemented here, because it's quite tricky, I repeat. So first, before studying this part here, I will eventually create a different solution in order to understand what are the problems in this case. And then we will study this that is already implemented. And it's also quite heavy. Actually, I'm not going to re-export this, at least the actual version, because it's quite heavy, and also it takes sometimes to import this in Revit, because there are several hundreds of elements that you must export and import. But nevertheless, let's turn off everything here. Let's start from the beginning. This is a common twisted tower approach in Grasshopper, so there is no particular, let's say, concept here to be discussed. It's just a base organic shape like a NURBS curve, which is this one, defined by these points here. So if you want to change something, this is the first parameter because it changed the whole shape of the tower. Then there is a vertical array of these curves, all the same, all equal. Then there is a scale which happens at each level with a different scale factor, which is managed by this graph mapper here. Then there is a linear rotation. In this moment, you see that the rotation is linear. So basically, there is some twisting occurring. It's not so visible because of the organic shape. So, but you can see that there is some rotation here. And actually, you can also recognize this if you look at the actual surface. You will see eventually this seam here that flows all along the vertical loft. This is actually a loft surface. And so this is actually the only thing that is telling us that this is a twisted surface, okay? Not the shape. The shape could also be derived by a sequence or curve that progressively deform, and you will have a twisted-like shape, but no topological twisting. Now we have a real topological twisting, and this is the main problem that we have in this definition, okay? So this is going to create a huge problem when we are going to define the facade system, okay? Now let's explore this like with a pretty simple approach, okay? So I'm going to take this surface out of the actual workflow, bring it down here in order to create some additional workflow. So what I want to do, I want to create a facade system along this surface here, this twisted surface. So the easiest way to create this is basically by tessellating or paneling the surface, okay? And the easiest way of creating a panel system in Grasshopper is to use the Isotrim method. So you can use the Isotrim for this surface. You only need to define what are the cut domains. And in order to do this, you use the divide domain square, and you get this result here. So this is the easiest way of paneling a surface. Each one of these areas is an independent surface right now. So if you see here, you have 100 untrimmed surface. The amount, of course, of resulting surfaces depend on the U count and V count. So if I set here a slider between 1 and 40, try not to exaggerate with this. You can also create striped vertical surfaces if U is set to 1. So U, remember, is the horizontal in this case, and V is the vertical. So sorry, U is the vertical because this is a vertical loft, okay? So if I divide the U direction, which is the vertical one, into one single span, then there will be no horizontal division along this surface. And if I divide also horizontally by one span, I get exactly the original surface. So you can increase these in order to have vertical stripes if you want, like this, or you can increase these in order to have horizontal stripes. If you increase both of them, then you have this paneling effect. And in this case, we already have 1,600 faces. So pay attention to this because this can be extremely heavy, okay? Actually, if we go on with this amount of subdivision, this is going to be also more heavy than the actual process that I have implemented here, okay? So I would say that for now, we don't exaggerate with this, the amount of divisions. What are always thinking about the workflow, okay? So this is not a Grasshopper course technically. So we are always thinking about the workflow. What happens if we use this method? It's not so evident, okay? But this is a topological cut that we are doing along this surface. So geometrically speaking, if we go and analyze this from a front view, sooner or later we can realize that, first of all, the height of these horizontal stripes is not identical, okay? And also you will notice that these horizontal cuts are not absolutely horizontal, you know, so that there might be some horizontal distortion. So if you want to use these cuts here as panels for a facade system, you will have lots of problems, okay? So this is eventually not a good approach because you are obtaining some kind of weird geometry. So for example, I am dividing this vertically along the vertical axis, like in 20 spans, okay? Which means, by the way, that we will have 20 surfaces, 20 horizontal stripes, okay? If I take a, let me see, we have here the 3.5 is actually the separation between the step of this array of columns, okay? And we have 20 count for the linear array. So we have 20 here and 20 here, but you see that there is no correspondence because the linear array is defining the amount of curves. So you get, this is the first one, and this is the 20th one. But this is actually not defining the amount of surfaces, the amount of repetition. This is defining the amount of segments or the amount of cuts that you want vertically. So you should need eventually, in this case, at least 21 vertical repetitions in order to have some correspondence between the lines and the facade dimensions. So let me grab, I need to know what's the final height of this tower. So we know that there is a 3.5 step for this array, and we are getting to 20 curves. So in order to know what's the final height, we must multiply 3.5 by 19. Okay. So if I do this, I also had this expression already implemented somewhere here. Yeah, it's this one. So I'm going to use it right here. So I want to multiply the actual floor height by the number of levels minus 1. So this is going to give us exactly the height, the proper height of this tower. Okay. Now, if I create a SDL line starting from the XY plane, and this is going to come out in the vertical direction by default, and the length is going to be this one. And so I have a line that measures exactly like the height of this tower. Okay. Now, if I take this vertical line, and I also have the surface here. Okay. So if I take this vertical line and use a perpendicular frames in order to divide this line using the same amount of division as the paneling that I am creating, okay, I have this horizontal division here. Okay, we have 21 frames. 21 frames means that we have 20 spans between two subsequent frames. Okay, so if we create a intersection, mathematical intersection between a B-rep and the plane, our B-rep being the original loft and the frames being, well, the frames. You see, let me hide also the curves. You see that these are actually even spans along the surface of this tower. Okay. Now, if you take a look, we have one span, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20 spans. Okay. These are the 20 spans coming from the topological cuts that we have created with the divide domain square and Isotrim. So you see that they are totally not aligned with the actual regular spans that we get from these intersections. So if you want to create a regular facade system, you cannot use the Isotrim, because in this case you are going to produce a totally irregular pattern of panels. So even if they are somehow rectangular, because they are deformed, distorted, non-planar, and so on, but they have this four-side aspect, they are not more simple than the hexagonal pattern that I've created along this surface. Okay, so pay attention to this detail, because when you work with organic shapes, nothing is actually simple, because nothing is linear by default. Okay, and also you have this kind of if you use the topological approach, which is this one, which is based on basically the topology. Whenever you see U and B, it means you are not considering the geometry but the topology. And so you are considering, for example, how fast this surface is basically being created along the vertical and horizontal direction, which depends on the topology of the original curves that define the loft. So there is no way of using this method for creating a regular paneling along this surface. Okay. You might also use this method that I am using here in order to create the first division. So for example, if you want to have at least a control over the horizontal divisions along the surface in order to be perfectly coincident with the actual floors, because remember that this thing here, it will also be affecting, you see this greenish wire that flows all through the definition, is going to define Revit levels. Okay, and so if you want to have some, let's say, correspondence between all of these things, then you should also consider that you need to refer to this value and also to this type of definition. By the way, you see that in this case, as I am, I clearly made a mistake here. I think it should be X by Y. Let's double check that we have this. Yeah, exactly. Now they are coincident. Okay. There is also an error here. Now you see that we are working on the edge basically because we are asking this component to create the intersection between an horizontal frame that is basically coincident with some upper profile. Or in this case, for example, the length of this line is overcoming here the height of this tower. So that's why you have this kind of error. But nevertheless, this is working. You see, there is only an empty branch for this data tree, which is something that you can eventually get rid of this by using a clean tree and remove empty, invert this. So it is set to true. And instead of having 21 branches, now we have just 20 branches, and they are all filled with one cross section. Okay, so if you do this, you have at least control over the horizontal subdivisions of your surface, and you can use, for example, in intersection, you will have a physical intersection surface split, where you can take the original loft surface and split it with these curves here. Eventually, I think that that grafting here, a data tree here is would not be working. So we get here 19 fragments, which are the horizontal stripes. But in this case, they are not topological stripes. Okay, they are physical stripes. So they all have the same height. And once you have these fragments here, you can eventually then subdivide them horizontally, which is something that you are reducing here the lack of control that you have with the topological approach. Okay, so keep in mind that even when things look simple, like with this approach here, you will have some consequences that eventually they are not immediately visible, because basically no one would pay attention to the fact that these panels are not perfectly horizontally aligned. Okay, when you see this pattern of four corner surfaces, but they are not aligned. So you must take this into account. And eventually this can be a first step towards a solution. I will not go on with this, or eventually, yes, we can, but keep in mind that the topological approach gives you untrimmed surfaces, which is good, while surface split, as is a trim, is giving us trimmed surfaces. And once again, if you, for example, try, now we are going to use the topological method in order to panel these things. So I'm going to take these fragments here. I am going to create here a data tree. So each set of 340 will be applied to each of these fragments. So I need to graft the panels before plugging them here. And I'm not going to use 20 by 17, of course. I'm going to use 1 by, I don't know, something like 3, in order to avoid a huge amount of panels, of cuts. And so you will have, let's double check here. You see, so see what happens. We are trying to divide we are trying to divide these fragments here, which belong to an untrimmed surface. I think nope. This is not good because I'm not getting. Oh yeah, because I think I unplugged something that was affecting the previous definition. Let's see. By plugging these fragments, I think I'm breaking the history. Okay, so we have these things here. So you see that basically the reason why is because this is also affecting the count of these perpendicular frames. Okay, so I must use a different slider here as I am eliminating the horizontal stripes. Okay, so these are the stripes. I'm going to feed them here, and I want to reduce these. So now here we have trimmed surface, which is correct. Each stripe is a trimmed surface, and this is dividing their domain into 17 parts. Let's lower this a little more, and let's also do something like this. Graph this and plug this, and let's take a look at the final result. So we have here one surface per branch, and we have 19 branches, and here we have 19 branches with 3 domain values. But you see that the result is not showing us like panels along the horizontal stripes. This is actually emitting, and let's see this with a panel. This is actually emitting 3 untrimmed surface, which is something that should give us sound like a warning. Okay, so 3 untrimmed surface 19 times. Okay, so if you take a look at this with a wireframe, there is something weird that's happening. You see that the whole tower has been split vertically into 3 vertical stripes, you see, and not the single horizontal stripe that we had. Why this is happening? Because these are trimmed surfaces, and the trimmed surface, remember, its original topology. This is something that eventually it's easier if I show you something like this in Rhino. So if we have this set of curves, like this one and this one, and I'm going to use this to create a loft surface. Okay, so exactly the same configuration, or more or less, it's going to be an open loft, but anyway. Now, if I take this loft here and create some line and trim with this line this part of the surface, and take this surface and activate the control points, I always see the original topology that is still reaching the original extension of the surface. This is something that is very useful in Rhino because this allows untrimming one object. So when you have a trimmed surface, you can untrim and go back to the original surface. Okay, but for us in Grasshopper, this is a problem. Okay, because this thing here is actually trimming the whole surface of the tower into 3 horizontal panels and 1 single vertical division. That's why we are getting here, you see, 57 vertical stripes. Okay, so how can we do this? How can we manage to divide a horizontal stripes into the panels that we need to bring inside Revit? Well, we must get rid of the trimmed surface. We must reach a status of untrimmed surface, because this would work with Isotrim. Okay, and so in order to do this, we must shrink a trimmed surface. Now, this command here belongs to pufferfish. Okay, so you need to have pufferfish installed in order to use this. And if you do this, this is actually going to shrink the surfaces. So here you will have untrimmed surface. Now, because these are horizontal stripes, we must we can expect, for example, that the shrink surface should occupy exactly the height of 1 single stripe. But we can do a quick check by baking these surfaces inside Rhino, take one of them, activate the control point, and see that the control points actually occupy the same height as the stripe itself. So if you go into the front viewport, you see that the upper line of control points is actually coincident with the upper edge of these stripes, which is exactly what we need in our workflow. So if I plug the shrunken surfaces inside the Isotrim, I will get finally horizontal panels, 3 horizontal panels. If you want more, of course, you can increase this and you will have more vertical division. What's the difference between this here and the original Isotrim that we applied to the surface itself? Is that we are controlling at least the horizontal separation between each stripe, which is actually corresponded with the floors of our tower. Okay, so you see basically that interoperability is one thing, but when you want to create things for the interoperability process, you must pay attention to a whole set of things that can happen in the parametric design workflow. Okay, especially if you want to achieve some regular results. Okay, for our sake, I'm not going to bring this thing further, because as if you pretend, for example, also to get to a more regular aspect for the vertical division of these horizontal stripes, it's going to be also an additional problem. It's going to be quite boring. So I'm not going to go through this, but nevertheless, keep in mind that you have this kind of situation with Grasshopper. Once you get these surfaces here that I'm going to consider as the final panels that we want to use, you can use these 380 untrimmed surfaces to do whatever you want, basically. Another way that you can use for defining a facade system in a parametric way, but with an interesting twist, could be to use tools like paneling tool. Paneling tools is basically a plugin, one of the historical plugins from Raja Issa, that allows creating 2-dimensional and 3-dimensional paneling system or patterns or whatever you might want to create on top of a surface. I do invite you to explore this, because it has also some let's say deformation tools for the grids that you create. So it helps creating some unconventional paneling systems. So it's worth exploring it. And there are also other methods that you might want to explore. From native Grasshopper installation, for example, you can also explore the twisted box approach, which is something that is based on deformation. So if you go into the transform toolbar, you will have the morph group of component, where you will find the box morph and surface boxes and so on, and twisted boxes and so on. So these are all deformation things. When you see morph, these are all deformation tools. But the box morph is actually what allows to create a 3-dimensional pattern over an existing surface. And you can use this for defining the panels on top of your surface. Also, remember that with the help of Grasshopper, you can create dynamic facades. So, for example, there are plenty of actual built example for this, but for example, dynamic facades that react to the intensity of the irradiation that they are getting from the sun, for example. So they close or open up some panels according to the level of radiation that they are receiving, solar radiation that they are receiving, or simply light intensity. Okay, so you can do this easily in Grasshopper and then export this to Revit. The trick is always create the more controlled geometry possible in Grasshopper. Okay, this has to deal also with Revit limitations that we were already discussing yesterday. There are some things that cannot be solved automatically in Revit. One of these things are the stairs. So by the way, let me open Revit in the meanwhile. One of these things are the stairs. So you see that Revit is not capable of solving the node between the stair and the floor automatically, or totally automatically. Another thing that can happen, for example, is the node between walls and floors. Now, we saw yesterday that this is actually not a problem. This was not a problem for our multi-story building. But the multi-story building is actually obeying to Revit's logic. And Revit logic is that floors are horizontal and walls are vertical. Okay, so this is how Revit sees things. Now, if you try to force Revit to consider, for example, a node between, for example, a floor and a wall with a variable inclination, okay, in that case, Revit simply cannot solve that intersection. Okay, we are going to see this eventually because I'm going to use, for example, this surface to define a wall. Okay. But this is going to happen later. So there are some things that simply cannot be solved by Revit or understood by Revit. So try to keep things the more regular possible. Okay. So this could be another approach to paneling. So in order to get a simple geometry, but and also try to solve some practical problems like having this division here corresponded with the level height. So you see that it is 3.5 meters. Okay, so this is going to be corresponded with Revit levels, which are, we already have the floors. So you can already see that the panels correspond exactly to the presence of one floor. So everything is working perfectly with this paneling. Nevertheless, remember that these surfaces here are double curvature surfaces because they are originally trims from a double curvature surface. So each of them has a specific shape and also is not planar. Now, planarity is one other aspect that we must take into account. Not because we cannot send non-planar geometry to Revit, but thinking about production eventually, you might want to work with more planar shapes. And this kind of geometry here is the worst scenario that you can have, because this twisted tower is like a deformed cylinder, if you see this, and there are some areas with a huge curvature value, like this one, for example. Okay, and also this one here at the base. Now, when you have this kind of situation here, it's almost impossible to planarize these panels and also maintain the continuity between these panels here and the adjacent panels. So in this case, you will have some actual problem as regards aligning the surfaces of these frames here, of these panels, if you want to planarize them. But nevertheless, this is something that it's worth exploring. So once we have the surfaces here, as these are untrimmed surface, we can also use something like the evaluate surface component, where we evaluate these surfaces, reparameterize them, use a multidimensional slider, leave this at 0.505. So right now, what we are getting is the tangent plane to these surfaces corresponding to the center point of the surface itself. So we are getting basically the center point of each panel and the orientation of each panel. Okay, this is the result with this evaluate surface. And if we have the frame, which is the tangent frame to the center of each panel, we can also do something like this. We can derive the wireframe of each panel, which is going to be this set of four curves per panel. We can join these curves together. So we have a set of 380, polylines, or polycurves in this case, because they are not straight segments, so they are not polylines. And then we can project these objects here onto these planes here. So if I take these curves, which are contained into a data tree, and here I have a list of 380 frames, I must graft the frames and plug the frames into this plane input. And as a result, I get these final objects here. And these final objects, you see that there is some, let's say, misalignment here, but they are planar. Okay. So if you want to work with planar panels, you can use these projected geometry, which are basically polycurves or closed planar curves, and you can use them for creating some boundary surfaces in order to double check that they are actually planar surfaces. As you can see, they are flat panels on top of this facade. Now, this is extremely good because this can be simply manufactured by using cut technology, which are cheap and fast, so you can reduce the cost for producing this kind of double curvature facade. Of course, you have some real problem, especially where the surface, the underlying surface has more curvature. The way you can solve this is eventually by increasing the amount of horizontal division. So reduce the width of these panels, because in this way you are basically reducing the variation of curvature from one panel to the other. But you are increasing the amount of panels, so it depends on what you want to do. In this case, you spend more in producing panels and less in calculating the frame, the mullions for this continuous facade. Because if you have this kind of deviation here, the element of the structural part of the facade must absorb this variation of for the inclination of this panel. So you must use a frame that is capable of absorbing this or connecting this panel to the other panel. So a thicker structure eventually. So whatever decision you take here, you must take into account this option. There are more advanced techniques that allow to create planar, continuous, and seamless patterns on a surface, but we are not going to go through this, of course, because it would take days, or well, at least a couple of sessions to explore this. But nevertheless, be aware that there are other solutions to this thing. And the other important aspect that I wanted to point out is that this panel, as this is a topological paneling, it is completely transparent in terms of the main problem that this surface has, which is the seam line. So if I, for example, extract the wireframe of the original loft surface, remember that there is this seam line here. But as this is a seam line, an internal seam line, parametrically speaking, this is the separation between the first panel and the last panel. So this facade system is actually respecting the topology of the surface. So there is no problem with this paneling method, okay? Now let's explore a different approach, which is the one that I have used for creating the actual paneling in my original definition. And this is going to create some topological problem that must be solved. So I'm also going to add all of these things to this group, which is going to be a variation on the main theme that we have. So this is one paneling type. Let's explore this other one. Now, this other one is the one that is producing actually these deactivated panels here. I deactivated them because they are pretty heavy to calculate. And also there is a mullion system for the curtain wall. So everything is turned off by default in this definition because it is extremely heavy. I prefer to concentrate on the base geometry. So the base geometry of these panels are these, which is a continuous pattern of hexagonal panels. Okay, you see that there is no trace here of the seam line, the actual seam line, which, by the way, it's here. Let me visualize this. Oh, I think I already got rid of this, but anyway, you already know that that's the seam line problem. It was this vertical line. But anyway, you see that we have this continuous pattern of flat hexagonal panels. Okay, so how can we create this? Because this is a little more challenging than a standard horizontal vertical pattern. And of course, we are not going to take into account the vertical spans that we have. So this panel is not necessarily aligned with the actual level height. Okay, it's basically impossible to align it because this is an hexagonal pattern. At some point, you should break the panels if you want them to be aligned with the frame, with the levels. Okay, so how this thing starts is by creating. You see that there is a duplicate surface here, and this surface is basically a skin on top of the original loft. So I took the original surface, or the original curves actually, created an offset of those curves by 1 meter, and then used these new curves to create the new surface for the actual facade paneling. Okay, so this is not the original surface, it's an offset surface. And I did this offset and not the offset of a surface because the offset of a surface depends on the orientation of the surface. So in these upper areas, the surface has this orientation, and so an offset would create a surface like this. So the top edge of the two surfaces would stay at a different height. Okay, and also here at the base, this is the orientation. The offset surface should be something like this, and you will have a different height for the skin and the actual tower inside. So that's why I prefer to offset the curves. And also, you can use these offset curves if you want to create the floor. So if you want to bring the floor on the facade, or if you want to have the facade over the floors, you can do whatever you want in this case. And then there is Lunchbox hexagonal pattern, which is an automatic component. Okay. And as always, when you have automatic components, always ask yourself, is this going to work or not? This works actually for the general pattern definition, but it gives you a huge problem along the edges. So you have hexagonal pattern on the inner part of the surface, but along the edges you have this kind of pentagons or something like that. And especially here where you have the seam, also you have pentagons here, and you have this kind of split pentagon here on these corners, okay, on the four corner of our surface. So two here and two here at the base. We must get rid of all of these divisions here. We can leave these as they are. There is basically no problem with that, unless you want to get rid of the non-hexagonal panels. So in that case, you will leave the base of this tower like with these openings, you know, which can also be interesting as from a design point of view. But the problem that we have here are these internal hexagons that are split into two halves, and we want to rejoin them together. Now this is tricky. Okay, it looks like very easy, but it's somehow tricky. Of course, there are other methods. You can also use scripting to create a seamless hexagonal pattern over a surface, but I wanted to stick to a standard Grasshopper workflow. Okay, but eventually with some plugins, of course. So these are the original hexagon cell, and here with this block here, the only thing that I'm doing, I am reaching this final seamless hexagonal pattern. As you can see, there is no trace of the actual seam line for our surface. Okay, so let's see how this is done. Let's go quickly through this. I exploded the cells, calculated the amount of segments that you get from the cells. You see that you have 4, 5. At some point, you will have 6 because they are the inner hexagon. And I am exactly checking if the cells have 6 sides. If they have 6 sides, this is going to be true. If not, it's going to be false. So all the cells that have 6 sides, which are the hexagons, are going to be in list A. If I take a curved component and plug list A, I only have the complete hexagons of my panel. All that comes from list B must be tweaked or adjusted. Okay? So counting the amount of sides, I separated the regular panels from the irregular panels. And then I use this plugin here, which is, well, this is actually, you cannot control Alt this because it points to a Visual Basic script, because actually this is a script, okay? But it belongs to Mesh Plus plugin. So if you go here to, well, which is this one? This is Mesh Plus, as you can see. And there are some comments here in order to create Energons, okay? So I want to create Energon meshes, starting from the vertices that we have from the irregular panels. So you see, this is Energon mesh, okay? And this is a very complex, well, not complex, it is a 3 times a series of things that you can easily understand. So there are vertices, faces, and edges. In this case, for example, I am calculating the amount of faces, because what happens with this Energon mesh, starting from the original polylines, which are basically the irregular panels, it creates this kind of thing. Okay, so this is what this thing is doing. It's creating Energon mesh, which are triangulated mesh, as you can see. Okay, with this center. Once I have these, I did, and this is another plugin. This comes from Mesh Edit. Okay, even if you can find this in the standard Mesh toolbar, and it's here, it comes from Mesh Edit. Okay, so you can command info. You can see that it comes from this library here, which is Mesh Edit 2. Okay, so eventually there's another plugin that you will need to run this this script. So Mesh Explode is actually giving us access to each of the faces of this mesh. So basically, we are getting triangular faces. You see that vertex is 3 and face is 1. 316 because we are talking about every single triangular face for these meshes here. And so I am calculating here the actual length. For example, here you have a data tree which contains the vertices of these meshes. So you see that if I take a look at this, you see that these are the indices of the vertices that allow creating the actual faces, the actual meshes that we have here. Okay, and so partition list, partitioning these faces here by the size of the vertices. So I am just subdividing the meshes between pentagonal meshes, quadrangular meshes, and so on. And then I am joining the triangles all together in order to have these actual Energon meshes made up of several triangles, welding them together in order to get rid of the internal edges, calculating the naked vertices, which are only the naked points. And finally, you see that here in this case, I am concentrating on these upper and lower problematic panels here, getting rid of the duplicate curves, as you can see here, eliminating the inner connection, and joining the rest of these curves all together. The result is going to be these two polyline curves. And if you apply the same method to also the other panels, like the panel along the vertical seam edge and the panel along the upper edge and lower edge, you will get to these panels here as well. And here are the internal regular hexagonal panels. So in the end, these two here are two applications of this same workflow here. And the first one is just the regular panels internalized. It's like having this exactly this container here. So it's list A. Okay. And so finally, this is how I got rid of the irregular panels along the seam line of my original loft. Once you have this, well, you're basically done, because the only thing that I was doing right now is planarize this panel. Remember that they are hexagonal cells, but on a double curvature surface. So you need to make them planar, which is something that I did exactly like we did a minute ago. These are the discontinuities. I was calculating the average point. The problem with the reason why I did this is because when you have this rectangular shaped panel, you can use, for example, the evaluate surface, because they are, topologically speaking, they are basically square panel or rectangular panel. So you can use this in order to create obtain the center point, and also the center orientation, so the frame, in order for obtaining the projection. Okay, but when you have an hexagonal panel, you cannot work like this, because simply you cannot obtain a nerve surface from a set of 6 points. So these are basically all the vertices of our hexagonal panels. Okay, you cannot create a surface from 6 vertices unless you want to use the patch command eventually. Okay, but I don't want to use a patch command because a patch is a trimmed surface once again, and we need an untrimmed surface here. So I took the average point. So you see that the average point is more or less the centroid of this panel. So if you take all the vertices and calculate the average of the vertices, you get this centroid for the hexagonal panels. And once you have this, I projected this point onto the original loft surface and evaluated the original surface in order to obtain the frame correspondent to the centroid of each hexagonal panel. Okay, it's a workaround because I cannot work with hexagonal surfaces in Rhino. And once you have this, you simply project the panels onto the frame that you obtain. Of course, you see that where you have more curvature, this thing is producing a messy result. But when the surface is more or less flat-ish, then you have a nice flat hexagonal pattern distributed on top of the surface. Then I scaled this down a little in order to create some separation to host the mullions of this facade. And you can do this, well, I did it with scale because it's easier. I already have the center of scale, which are basically the average point. The geometry that I want to scale are the flat panel, but you can also offset this original panel if you want to control better the separation between them, because the scale is basically producing a non-uniform separation, as you can see. But it's just substituting the scale with an offset. And then this boundary surface is creating the actual surfaces for these panels. And finally, we have the extrusions with the actual thickness for these panels. And here they are. 10 centimeters. Quite a thick panel, but at this scale, you see it's quite light or thin. And then, well, there is the actual thing that we already know. This part is not actually, let's say, updated, this part of the definition. So I didn't use, for example, for the floors, the new Revit material layer component. But as regards the panels, well, let me activate this. You see, it takes some seconds to calculate them, and here they are. The only thing that I did here was simply subdividing the original set of panel into 2 separate sets, but randomly. Okay, so this is a random set of panels, and this is another random set. Well, the opposite. And so one is glass, and one is, well, some light metal, for example, or some matte material. So you have this kind of semi-transparent facade. Okay. Which is what I have already imported in Revit. So let's also open Revit Tower. Okay, here it is. So if we take a look at this from the cross-section point of view, it is this one. You see that there are bluish and whitish panels. You can give each one of them the proper material that you want. Of course, here I'm using glass, aluminum, which are not found in Revit material library, so there is no correspondence. But nevertheless, it should. If I switch, for example, to a realistic, eventually, no, they are all matte panels because they are just fancy material. Okay, so not going to create a ray trace because it's going to take forever. But yes, this is the shaded viewpoint. So this is what I did here. As regards the structure of this facade, these are the mullions, which, by the way, is turned off because there are quite lots of mullions, and I do recommend that you eventually export them only when you are sure that everything is going to remain more or less like in the final version, because importing these as they are 1,500 mullions is going to take forever in Revit to complete the import process. Not the panels themselves. The panels themselves are not that much. They are more or less 500. So It's not that time consuming, but the mullions, yes. And what I wanted to show you is this. Now you see that this is actually a curtain wall, basically, or a continuous facade. But take a look at how it is exported to Revit. We are using framing, so like beams, exactly. And the usage here is set to other, okay? Now, if you go inside the Revit toolbar, you will see that here there is actually no particular element that is capable of exporting mullions in Revit. If you go into architectural direct shape and you browse the type, you see that there is curtain wall mullion. But this is something that I found out. They are not imported correctly in Revit. So, I mean, you can define them here properly, like with an architectural direct shape, defining them as curtain wall mullion, but when you import it inside Revit, they are not imported. Okay, so there is something here missing. I already spoke about this with John, of course, and he's going to take a look into this as soon as possible. But he always told me there is a workaround. You can use standard framing, and actually it works. Okay, so you see that these beams here are not actually beams. If you define other, basically you are bypassing Revit controls over the actual aspect of a beam or actual function of a beam. So you can use this, and you define the standard Revit framing type, giving this name, and also defining the proper cross section. In this case, I have defined a custom profile because I want a standard square cross section, like 10 centimeter by 10 centimeter, and square solid 10 centimeters. So you must provide a surface in this case. We can also take a look at this from the top viewport. Let me see, where are we? Yeah, it's here. Okay, so it's this one. And the thing here is that, remember that in this case, for example, I also wanted to show you something. If I define this custom profile, remember that there is always a justification here that allows defining what's the alignment between the cross section or the Revit profile and the actual axis for our beams or our frames. Okay, but if we go and double check this at the mullion level, like this, and take a look at the axis. Let's see if I can see this properly. Some point it should be easier. It depends on the orientation, but you see that actually these objects here are not even close to stay in the mid of the cross section is not actually close to the mid to the axis line with its center point. So the way that this plane surface is defined is not correct, because you should have this square with its center in this point here and not its corner. An easy way of doing this, very easy way, is to create a symmetrical domain, which is a heteroptera component. So this is the plugin, once again. You define the length of the domain, which is actually the actual size that you want for your geometry. And the base is 0 by default. So you are creating a domain which is minus half the length to half the length. So this is going to be minus 0.05 to 0.05. And then I can eventually disconnect this from here, transfer these wires to here, and use this like the domain range. And you see that now the square is centered in the origin of this coordinate system. And this should also make these mullions more regular, because you see that now they converge in the intersection point of these axis lines. Okay, so pay attention. In order to define things properly, you also have to double check, well, basically almost everything along the workflow. So let me substitute this. Remember that this is Heteroptera plugin again in action. And also there is something here that I want to also to point out. This is the remove duplicate lines from Caramba 3D. Now, remove duplicate lines is a utility that is present in several plugins. It is also present in a standard Grasshopper plugin, which is actually included in Grasshopper install because it comes with Rhino 6, which is Kangaroo. So if you go into Kangaroo, not 1 but 2, you see that between the utility commands you will find the remove duplicate lines. Okay. I noticed in this particular case, if I put a flatten here, okay, I noticed that in this case, if I try to use Kangaroo remove duplicate line, I get here 2968. Here I get 1502. Now, of course, this is something that affects our workflow, well, in an important way. The reason why this happens is because we have some tolerance control. Remember that in this case, I am using as the original curves, I am using already the projected curves. So there is this, let's say, deviation between the frames, okay? And I don't want these frames to be twice the amount because I have this deviation. I need just one mullion between two panels, okay? So there are several things that you can do here. You might want to use, if you, the remove duplicate lines from Caramba 3D, instead of working with a tolerance, which is a percentage, which give you no control over when two things are going to consider as one, it has a limit distance. So you can physically define under what circumstances two different lines are going to be removed, but in terms of distance, which is more effective. Okay, that's why I use this one. But if you want to use this and you don't want to use Caramba 3D only for this component, which somehow can be stupid, you can also refer to the actual frame or lines coming from the first definition of the frame for this structural for this continuous facade. So you can refer to these lines, which are actually coincident along the edges. You can explode all of them and then remove duplicate lines with Kangaroo, which is going to work. Okay, but under this circumstance here, this is going to do the job. And so this is going to define the axis. And then there are the profiles. Well, we already know them. And basically, that's it, because the usage is set to other. And so we are producing this set of 1,500 mullions for this facade, which, by the way, in Revit are correctly exported. Now, I think this is the wrong export, actually, because the mullions should not be exactly coincident. Oh, yes, I already did this trick, but I forgot to save the file eventually, because I see that the mullions are converging into the node. So yes, I think this is the correct action, fortunately. Also, we can see this from a floor plan with a fine detail. You see the mullions actually they are sectioned here. And it is rectangular because it has an inclination, but the cross section is square. So here's the square solid 10 centimeter, which is defined like here, the name of the profile, which also you see the edit type gives you access to all the properties, or you can also see this at the instance level. At the instance level, you will have the actual length for these elements. So they can perfectly be used for schedules and quantities. Okay. Let's go back to Rhino. So this is the curtain wall. Let's call it like this. Let me well, actually, no, I don't want to turn this off because I also want to show you this part here. This is going to take some time to update the definition, but it's worth the wait. Okay, so let me turn off also this, and let me show you what we have here inside. Always regarding the facade and the production and so on, because in Revit it's very easy to calculate, for example, the with scheduled quantities, you can create costs and create, for example, or classify this or catalog these panels or mullions or whatever. But in Grasshopper, you can do some other things, and this is something that we are going to see in about 1 minute, because it takes more or less 1 minute to update. So sorry for this, but this is going to be a process that allows to rationalize the paneling of our surface. It is based on 2 plugins. First one is Lunchbox again, the machine learning part of Lunchbox, and the other one is a simpler plugin which is called OpenNest, which is useful for manufacturing. And as we obtain flat panels, we can organize the production by using OpenNest, organizing the panels inside an area in order to send them to a production process. So let's wait for this to appear. It's going to be colorful, as you can see from the gradients. This somehow also is also corresponded to an observation from John himself. When I was discussing with him, you remember the custom parameter defining the unit price or the unit cost for some element that was not possible. It was not possible to use it in Revit because it was missing the proper units. Like for example, the currency per meter, for example. John was saying, okay, there are some things that it's worth doing in Grasshopper, and this is one of them actually. I don't agree with the cost analysis. I would say that cost analysis is more effective to do it in Revit, because in that way you unify all the scheduled quantities evaluation inside one single platform and not producing documentation from 2 different platforms. But here it's totally worth, because in this case, in order to organize production, this is something you cannot do in Revit. So let's see what happens here. I used Lunchbox. If you go here in Lunchbox, you will find machine learning group of set of components, and there is the key means clustering. This is a component that is capable of grouping things according to a specific property that they share. Okay, and in this case, what I did was calculate the area of the panels, the surfaces, the original surfaces. I calculated the area and used this area as training inputs for this, well, let's call it machine learning component. It's a very basic level of machine learning, by the way, but it does the job. It only asks for a couple of inputs. So what are the training inputs? So what are the values that you want to take into account for creating the grouping, and how many groups you want to create, number of clusters. Now, I decided 10 because the area, the surface of these panels is extremely variable. You have very small panel and a very large panel, which are the red ones. Okay? So the result is a set of indices. It's not the actual surfaces or the actual values for the areas. It's just a set of indices. And these indices establish whether a particular value between these falls inside one cluster of another. So this is actually the cluster, the number of the cluster. So 0 is the first cluster, 3 is the 4th cluster, and so on. So you will have 9 values coming out from this thing here. And if you want, you can use a custom preview in order to give a quick visualization of the panels by area. Okay. So for example, here I took the result, which is a set of values between 0 and 9. Okay. Calculate the minimum and maximum, which is going to be, of course, 0 and 9. This is another heteroptera component, by the way. Use them as lower limit and upper limit in order to establish that 0 corresponds to blue and 9 corresponds to red. And parameter is going to be exactly the cluster number. Okay? So when an object belongs to cluster number, I don't know, 4, is going to be more or less yellow. So this is the mean value, the average value for the area that corresponds to these panels here. And I am visualizing the panel, the actual surfaces, with the correspondent color coming from this gradient here. Okay, and moreover, what I did is explode. Well, actually, this is not an explode. This is called unweave. So I took the actual surfaces on the facade and unweaved them. It means separated them according to this cluster pattern. So in this way, what I did was basically separate the panel by area, okay? Because I'm using the cluster number, and the cluster corresponds to a specific value for the area, okay? So if the area of one panel is more or less equivalent to another area of another panel, they fall inside the same cluster, and so you can use the cluster number for unweaving the list of panels. So we have here 53 panels, which are the smallest one, and here we have 62, which are the largest panels. So if you want to see them, here they are. These are the largest panels, and these are the intermediate areas, and you have all of them divided by area, which is very useful in order to understand where you are, where these panels are located on over the surface of this tower. Okay. I did the same thing, unweaving with the same pattern. This time I unweaved the frames. And you might wonder why, because I was then reorienting the panel on the horizontal plane in order to use OpenNest, which is another plugin, which is the one that was taking, well, 2 minutes actually, in order to optimize the positioning of the panel inside a flat sheet of material. This is important to for production purposes. Okay. Of course, this is the basic execution of the OpenNest. You see that there is a huge amount of space between each panel. And this can be optimized by defining the spacing that you might want. In this case, it's set to 1. So by default, we are considering 1 meter between two adjacent panels. This can be lowered to as low as you want. It can also be 0. And then you can define how many rotations you might want to perform for optimizing things, how many iterations. This is the lowest amount of iteration is 1. I didn't increase these values because I don't want to spend more than 2 minutes to see the result. Actually, this is going to be to be turned off by default. But nevertheless, you see that also after the optimization, you can still recognize the panel by their area. So it's very easy to name or to label these panels after the optimization and placing in this production workflow. So if you want to see this, we have the largest panel over the surface itself, the tower itself, and the largest panel where they are located during the optimization process. So you can give the same name to this and this in order to recognize them. Okay, so this is one thing that is always about production and building and execution of this project, actually, but you cannot do this in Revit. You must do this in Grasshopper. Okay, so there are some things that you simply cannot do with an interoperability workflow in Revit. So it is recommendable to focus on Grasshopper. So easiest things, levels. You see in this case, just a quick note, I start from level 1, so the start value for this series is 1. In this way, during the import in Revit, the actual level 1 already present in Revit will become the ground floor in Revit, okay? Because it will have the 0 height. So this is the only thing about levels, nothing important. Then we have the usual definition for floors. Actually, this is, as I was saying, this is the old Revit material. We can quickly complete this by substituting this with the new, material layer, which allows to define also the core layers for a floor. So Revit material is going to remain this, thickness is going to remain this, and function is going to be structure, but I'm going to add a Boolean toggle. Core is going to be true, and structural is going to be true as well. Remember that this structural thing affects the floor plan visualization that we saw yesterday. Okay, and so I'm going to use these as oh, you see, this is interesting. Take a look at this. This is the old floor type. Okay, and in the new versions, you see that the new floor type doesn't have layers above core, layers core, and layers below core. So in this new version of the plugin, they got rid of this definition for the layers, material layers for this floor type, and they had to switch back to this core thing here. So here it was clearer. According to my opinion, it was clearer because you simply plug the layers that you wanted above the core in this input, and then you have the core and layers below. Now, this order here from top to bottom is maintained, but you have to remember that you must plug the layers in order from top layer to bottom layer, specifying if they belong to the core by using this toggle here. Okay, this is the old version. Okay, so that's why here there was no problem with defining the layer core. But anyway, nevertheless, this material layer, you can plug it either here or you can plug it here in the new floor type definition. I'm going to leave this like this double alternative that we have. Let me move everything down. And so eventually you can, well, let's get rid of this old material layer definition, and we can simply collapse this thing into one single group. Okay, just see this is an evolution of this plugin that we would assist in like live, basically, more or less. But yes, you see that there are some adjustments that were made. So these are the floor, actually, one single layer. I don't want to waste time with defining other material layers. Here are the framing. Now the framing is, you see, it's just an excuse, of course. Structurally speaking, this has no meaning. Okay, so don't rely on this as if it was a structural study. But once again, I used the incessant network from Heteroptera to create this kind of non-conventional interconnections. Okay, so this is the command that is creating this kind of connections here. Of course, you can also do something more, let's say, aggressive, you know, if you want. And you can also, in order to avoid this intricate system of connections, you can also always tweak the distance. So if you take a 5.00 slider, you are limiting the connection range, and you see that we avoid, even if we are allowing 5 connections, at the highest floor, as the separation between the end point is more than in the center of the tower, then you have very few connections, okay? But if you go here, this 5 is enough for creating this intricate system of connections. So this is something that is not the perfect solution to creating this automatic interconnection. But if you want a quick result, it's very easy to tweak these values and have an elegant solution, as you can see. Not a proper one, but at least something that seems to work at each height the same way. Okay, so if we hide the floor, you will recognize that there is a rotating pattern of connection. But nevertheless, this is something that needs absolutely needs more tweaking and some adjustment. And the Revit framing type definition, we already know this. It's basically the standard workflow that we already observed. And then there are the columns. Now the columns is simply data manipulation in Grasshopper. So we only have this scaling once again from the actual original curves, because I wanted to create 2 rings. Let's call them so, two rings of columns. Okay, so I divided these. I flipped the matrix because this division belongs to each curve. So now after flipping the matrix, we have the same points, but they are sorted vertically. And then you can create polylines and create these two vertical connections. They are polylines, so each segment starts from one level and ends at the upper level. So if you explode them, you have automatically the axis of the columns. There is another flip matrix here, because if you don't do this flip matrix here, you would be grouping columns by position or by row. So basically, if you plug this directly here, you will have a line of column belonging to different layers or to different levels as from the building point of view. So if you reflip the matrix, you have the same connections, but now they are sorted like horizontally. So here you see that you have 8 columns. Here you have other 8 columns. And these two sets of 8 columns, they both belong to the first layer here. Okay? So that's why there is another flip matrix. And these lines here are going to be converted into the actual Revit column. There is something that I didn't do here, and this is actually something that we should take into account, which is adjusting the orientation of this column. Okay, the orientation should depend on the curves that we have used. This is something that we already saw. The moment you do this divide curve, you also have the tangents. And you can use the tangents in order to derive the orientation of the columns. Now, actually, you see that we went through a flip matrix and other flip matrix only because it's easier to create all the column axes with a single polyline. Okay, that's why I did this flip and reflip. But in the end, if you flip and reflip the values, you are just going back to the original set or data structure. Okay, so you see that this thing here is actually 19 branches, each one containing 8 axes. And these are other 19 branches, each containing 8 values. So the axis is going to be 19 branches with 16 values. And here we have 19 branches with 8 values for the tangents and 19 branches with 8 values for the tangents of the inner curve. So if you take these vectors here and plug all the tangents from these and from these, we will have a single data tree with 20 branches actually and 16 values. And this is 19 branches. There is something weird about this. Oh yeah, no, it's not weird. It's that here we have the division at the curve level. So the curves are ranging from ground floor to the top of the tower. But then we are reflipping here just the lines, and the lines belong to the spans. Okay, so there is if the spans are x, the curves are x plus 1. So that's why we get 1 branch less than in this case. So yes, we cannot do this automatically by plugging the orientation as the origin of tangent vector. Eventually, what we can do is to, let's say, remove the last branch from this tangent data tree in order to don't consider the upper curves tangency. They are not useful because our columns start from one floor and reach the upper floor. So in this case, the orientation must be defined with this floor, not the last one. And so we can get rid of the last value here. And it means eliminating the last branch. So we should go into sets, go into tree handling, and eventually, let me see if we can easily do this. Yes, I think a split tree would work. Or we always must provide the path. So it's never a pleasure to work with tree. Let me see if I can do this in a quicker way. Because you see, for example, that each time you update Rhino, as Grasshopper is now part of Rhino, you also have some new components popping up in the Grasshopper toolbar. But I would say that the most efficient way right now seems to be the split tree. Yeah, I think yes. I was just watching if I can use, for example, a sub tree or something like that, but no, there is no such command yet. So yeah, split tree. Let's see if we can easily manage to do this. So using path masks, so we must understand what's the actual mask of this. We must know this from the param viewer. So we have a visual understanding of the structure. So the mask is going to be 0, 0, 0. We must define this as a concatenate value because I want to split here at 0, 0, 19, the last branch. Okay, and as this is variable because 19 depends on this value here, then we cannot simply create a mask by defining 0, 0, 19 and then plug it here. Okay, so let me see if I now quickly do something like this. Sorry, 1, 2, 3, and then 0, 0. Let's do it this without parametric approach for now. This is a text, and we should have positive and negative. So we have 18 branches, which are 19 at the moment. So we have 19 branches here, each one with 8 elements. So the only thing that's being stripped out is the 8 tangents for the last curve here on top. Now this is not correct because if you change the number of layers of levels, this will not work. Okay, so keep this in mind. And of course, we must also do this for the upper tangents. So now, yes, we can use a vector. And well, we need to use the negative, plug it here. So we have one data tree with 16 elements per branch, and we can use this as orientation. So plug this here, and this should affect the columns like in the proper way. We could eventually take a look at this from top. Well, no, top is not the best option, but yes, it should have created some. You see that now the body of the beam is always aligned with the actual curve. We can also double check like this. Yes, exactly.